So welcome to the first of two higher level units within the topic of structure and bonding. The first one focusing on covalent bonding and structure. So by the end of this unit you should be able to discuss covalent bonds as an overlap of atomic orbitals and have appreciation of sigma and pi bonds. Know about formal charges and how to calculate them, and know about exceptions to the octet rule, including some species having incomplete octets or even expanded octets. So you should also be able to predict about sigma and pi bonds and whether they form, deduce Lewis structures from molecules, valence electrons up to 6 electron pairs, apply formal charges to ascertain which Lewis electron dot structures are preferred, deduce using the HL electron pair repulsion theory, the electron geometry domains of these particular Lewis diagrams, and focusing on ozone, explain the wavelength of light required to dissociate oxygen and ozone, and describe the mechanism of the catalysis of ozone depletion around CFCs and nitrous oxides. The first thing we're going to look at is the concept of formal charge, or FC. So formal charge is the amount of valence electrons minus the half the bonding electrons minus the non-bonding electrons. So essentially it's the formal charge of a Lewis diagram or a species. Okay, so to determine the most favoured Lewis structure, we've got two options. You choose the structure which has the formal charge closest to 0, or the structure, if it is indeed charged, with a negative formal charge on the most electronegative atom. Okay, so you might be given a range of different Lewis diagrams for a structure, and you've got to choose the favoured Lewis structure. So let's look at an example, determining the formal charge on the following cyano compound which we have before us. So the first thing you have to do is work out the formal charges on each of the atoms. So the formal charge is equaling to the valence electrons minus half the bonding electrons minus the non-bonding electrons. So for nitrogen, which we'll start off with, the amount of valence electrons is 5, because nitrogen is in group 5, it has 5 valence electrons, minus half the bonding electrons. Okay, so remember this line here represents three sigma bonds, which each have one electron, which have 2 electrons. So it's going to be 6, so it's going to be 5 minus 3 minus 2, because you've got this non-bonding pair of electrons here. So the formal charge on the nitrogen is going to be 0. Okay, good old 0. The formal charge on the carbon is going to be 4, because that's the valency of carbon, it's in group 4. This time, minus 8, because we have 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons. Okay, so it's going to be 4 minus 4, and as you can see, it hasn't got any non-bonding electrons, so it's going to be 0. And finally, we have the formal charge on the sulfur, which will be 6. Okay, that's the valency of sulfur, minus half times the 2 involved in the sigma bond with carbon, minus 6, because we have these wonderful 6 non-bonding electrons here, so it's going to be minus 1. So the formal charge of the whole species is going to be minus 1. So the question then asks is that you can have different resonance forms, which we've actually looked at previously in the other unit. So which structure do you think is correct? So looking back on the rules, which we looked at on the first slide when we looked at formal charge, the rules stating around the formal charge has to be either 0, which is not, okay, so minus 1 is the formal charge. The next rule says, well, it has to be on the most electronegative atom. So which one's the most electronegative atom? Well, the electronegativity of nitrogen is 3 and sulfur is 2.5, hence the formal charge is best placed on the nitrogen. Okay, so it means that this formula here, Lewis diagram here, is the correct Lewis diagram for it. Therefore, the bottom structure is the correct one. So problem number 2, determine which is the preferred structure. Okay, so when you're thinking about this, going back to the rules, it's all about formal charge first. The first thing we have to do is look at the formal charge. Okay, the formal charge on the boron is 3. Okay, because it's the valency of boron minus a half plus 6. Okay, because you've got your 6 electrons around the sigma bonds here. So 3 minus 3 minus 0 because there's no non-bonding electrons. So it will be 0. And the fluorine will be 7. That's the valency of fluorine. Half times 2 from the sigma bond again. Okay, minus 6. Okay, because you've got the 1, 2, 3, 4, 5, 6 non-bonding electrons. So it'll be 0. So in that particular case, the formal charge on each of the atoms in the molecule is 0. Whereas if we look at the Lewis structure on the right, one of the fluorines has a formal charge of +1, and one of the the boron has a charge of -1. So even though the molecule has a formal charge of 0, the atoms inside it don't. And going back to our rules, the first structure has the most atoms on 0 formal charge, is the most favored, so that is the correct structure. Okay, so this guy here is the correct structure. You can also use valence shell electron pair repulsion theory with expanded shells. So elements in the third period, elements from all the way from aluminium down to across to argon and below can promote an electron and have more than 4 electron domains. This is called an expanded octet. So the example I've given here is phosphorus. Okay, so you can have neon, 4s1, 3p3, and then it can promote an electron into the d orbitals to have 3d1, making PCl5. So that does change the shapes that can possibly form, because 5 electron domains, the non-bonding electrons in the equatorial positions of a trigonal pyramidal shape. And if you have 6 electron domains, as you go down, non-bonding electrons in the axial positions of a octahedron or a square pyramidal can form. Okay, so in terms of the trigonal pyramidal electron domain, there are 2 possible options for this geometry. You can either have an axial or an equatorial. So non-bonding electrons pairs fill the equatorial bonds first because they are only repelled by 2 bonds. Okay, whereas axial bonds are repelled by 3 bonds. Okay, so essentially if you have your electrons filling in the axial bonds, okay, and here, okay, if the non-bonding electrons form here, then you're going to have repulsion from this guy and this guy and this guy. Okay, whereas if it's only in the equatorial position, here we go, like that, say this is non-bonding pair, then you only get repulsion from that guy and that guy, only in 2 positions, so there's less repulsion. So in terms of the trigonal pyramidal electron domain continuing on, you must also never forget that non-bonding electron pairs also distort the angles because there's more electron repulsion. And we see this here with sulfur pentafluoride, where the angles of are not quite 180 degrees between the sulfur and fluoride here. They're 186, and you notice that this bond here gets crushed to 116 degrees. Okay, remember our rules around non-bonding pairs and bonding pairs and how they affect the structure of a molecule. So these are this table here highlights the different trigonal pyramidal electron domains it can have. So you have the 5 total electron domains, which are trigonal pyramidal, but they can be broken down into 4 distinct different geometries. Okay, so if you have 5 bonding domains and no non-bonding domains, then you end up with a trigonal pyramidal, and the classic of that is PCl5. If you have a non-bonding pair, then that's going to affect the shape of the molecule because of extra repulsion by that non-bonding pair here repelling against B. Okay, so you'll end up with a seesaw kind of shape. SF4 is an example of that. If you increase non-bonding mobanes to 2, you end up with a T shape, again because now you've got more repulsion between the two non-bonding electron pairs. ClF3 is an example of that. And if you have 2 bonding domains and 3 non-bonding domains, then you end up with linear because the 3 non-bonding domains here want to be all on the same axis, so they reduce their repulsion. And an example of that would be xenon difluoride. So in terms of octahedral electron domains, that's 6 electron domains in total. If you have 6 bonding domains and no non-bonding domains, you get a standard standard octahedral arrangement. Okay, so SF6, classic for that. If you end up with 1 non-bonding domain, you end up with a square pyramidal because you want to have the maximum amount of, or maximum reduction of repulsion from that non-bonding domain. And if you have 2 non-bonding domains and a bonding domain, you end up with a square planar like xenon tetrafluoride because you want to have these 2 non-bonding electron domains as far apart as possible. So overlapping orbitals are an important aspect of structure and bonding, and today we're going to look at both sigma and pi orbital overlap in relation to structure. We've already looked at this in some detail, looking at the resonance structure of benzene. So a sigma bond results from the axial overlap of orbitals, and a pi bond results from the sideways overlap of p orbitals in particular. Okay, so double bonds form by 1 sigma bond and 1 pi bond, and triple bonds form by 1 sigma bond and 2 pi bonds. So if we look, for example, at a carbon-carbon single bond, that would essentially just be okay, the orbital overlap of 2 p bonds, okay, head to head, okay, on the px axis, okay, and then you've also got these p orbitals overlapping here. Okay, so the interaction and overlap of these electrons here would be your double bond, and the interaction of the orbitals above the internuclear axes here, okay, so here would be your triple bond. So sigma bonds. So as atoms approach each other, here you have a region of orbital overlap. Sigma bonds are characterized by head-to-head overlap and the cylindrical symmetry or electron density about the internuclear axis allows for this. Okay, so you can have sigma bonds between s orbitals and p orbitals, and between p orbitals along the x-axis, as you can see here by the images. A pi bond, however, is characterized by side-to-side overlap of the p orbital lobes, okay, above the internuclear axis. An electron density above, so essentially it's electron density above and below this internuclear axis. So single bonds are always sigma bonds because of the greater overlap, and it results in strong bonds, which are energy lowering. Okay. In a multiple bond, one or more of the bonds is a sigma bond. Oh, sorry, only one of the bonds is a sigma bond, and the rest are all pi bonds. Okay, so carbon double bonds are an example of that. You have 1 sigma bond plus 1 pi bond. Or in the case of nitrogen, you've got 2 pi bonds and 1 sigma bond. So if we look at the bond dissociation enthalpies and bond lengths of some bonds, you can see from the red arrow I've pointed out the weakness of this extra bond. Okay, so a sigma bond is 364. A sigma bond plus a pi bond is 602. So it's an extra 140. Yes. No, 240. An extra 240 kilojoules per mole. Not quite the same as just one sigma bond. This is because the electron overlap is weaker, yet it is still an extra bond, so it still requires energy to break. Okay, so again, if you go from 602 to 835, it's about 235, not quite the same size as a carbon-carbon sigma bond, single bond. So also note the smaller bond lengths, and therefore they also have greater bond dissociation energies. So just to finish off, we're going to highlight the idea of functional charge and energy associated with double sigma and pi bonds around ozone. Okay, so bond order is related to resonance, but first, bond order is a measurement of the number of electrons involved in a bond between two atoms in a molecule. If the bond order is 0, then there is no bonding. So the bond order is the total number of bonding pairs divided by the total number of possible positions. So let's first work out the bond order of ozone, O3. Okay, so we've got O, O, O. So what is the bond order of ozone? Okay, so you should have an idea, should be pretty much something like this. So it's got 1, 2, 3, 4, 5, 6 around the oxygen, so it must have one more there. It's got now 8. It's got 1, 2, 3, 4, so it means it must end up with 2 around there. And it's got 1, 2, 3, 4, 5, 6, so it means it must end up with something like that. So from that, the total number of bonding pairs is 1, 2, 3, okay, and the total number of positions is 2. Okay, so the bond order is 1.5, and there is actually a resonance form for it as well. So problem 2, determine the bond order in this species. Okay, so you should have worked it out that the total number of bonding pairs is going to be 1, 2, 3, 4. Okay, that's pretty straightforward. Total number of positions is 3, so it must be a bond order of 4/3. So the importance of ozone. Ozone at ground level reacts with chemicals to form smog. Harms your breathing systems, or respiring systems, and degrades materials down. Okay, ozone in the atmosphere is important for life, essentially because it absorbs UV radiation and cosmic radiation from the outer space, okay, and from the sun, which can cause cancer. And exothermic reactions can cause a temperature inversion in the stratosphere, and this layer prevents convection, keeping the layers of the Earth's atmosphere stable. Okay, so it's very important. So oxygen requires photons with more energy, as ozone only has the energy of 1.5 bonds. We've looked at the bond order calculations, but also from our understanding of resonance forms, we also know that ozone does not have complete double bonds. They are only 1.5 bond order. Okay, so oxygen plus UV radiation with wavelengths which are less than 242 nanometers gives 2 oxygen free radicals. And ozone with UV radiation of wavelengths less than 330 nanometers then interact with form oxygen plus, again, free radicals. Okay, and we don't really want that to be happening. So the idea is that the ozone interacts with the UV radiation from the sun in the atmosphere and forms oxygen and free radicals. So the equations going back to the start of the year, of course, are the following to work out ultraviolet and oxygen ozone bond calculations. So I will leave them up there for a while for you to look at and remember, because we're now going to apply them in the next. So the bond energy of ozone is 363 kilojoules per mole. So calculate the wavelength of UV radiation needed to break this bond. So pause the video now and see what answers you can get. Okay, so the energy of the photon will be 363 kilojoules per mole. Okay, so that's what we've got here, divided by the number of moles, okay, which will be Avogadro's number. So you should get 6.03 times 10 to the negative 19 joules per photon. So energy of the photon will be Planck's constant times the frequency. So if we rearrange that equation, we get frequency equals to the energy of the photon divided by Planck's constant, which will give us a frequency of 9.09 times 10 to the 14 reciprocal seconds. So if velocity equals frequency times wavelength, we rearrange the equation with wavelength being frequency divided by velocity, wavelength equaling velocity divided by frequency. We'll rearrange the equation that way. So 3 times 10 to the 8, because the speed of light, divided by 9.09 times 10 to the 14 reciprocal centimeters or hertz, will give you 330 nanometers. So UV light breaks the bonds in oxygen to create free radicals, atoms or molecules which are unpaired valence electrons and so are highly reactive, which we'll look at in a little bit more detail in organic. So oxygen plus UV radiation with wavelengths less than 242 nanometers will give 2 free radicals, which then undergoes an exothermic reaction with the free radical reacting with oxygen to form ozone. And the reverse also occurs, creating the ozone cycle. So ozone plus UV with wavelengths of 330 nanometers, you have oxygen plus the free radical, and that free radical interacts with the ozone to form oxygen back again. So there are, of course, ozone destroying chemicals. There are CFCs, which can catalyze the breakdown of ozone, and also nitric oxides, which come from motor vehicles, especially in industry, which catalyze the breakdown of ozone. These compounds are also free radicals and have complete octets, and hence are highly reactive. So in terms of catalytic ozone destruction using nitric oxides, the balance of the ozone cycle can be disrupted by depletion of ozone from either nitrous oxides from factories and so forth, by this equation here, by formation of nitrogen dioxide free radicals. And what happens is the nitrogen oxides slowly diffuse their way from the troposphere, and aircraft fly in the lower stratosphere, causing direct ejection of these nitric oxides from their combustion. And NO can last from about 22 to 111 years before actually breaking down, so quite insidious. So just to summarize how chlorofluorocarbons work, again they form a free radical, again through UV radiation by this propagation here, and as with NO, the chloride free radical catalyzes the decomposition reaction of ozone into oxygen. And we don't want that, we want ozone to stay. Okay, so that's pretty much it in terms of higher level around covalent bonding and structures, and move on to resonance and hybridizations next.